Hello and welcome to Extreme Academy Live. This is where you come to advance your knowledge, advance your skills, and advance your future. This is lesson 3 out of 8. And at the end of this course, you'll be able to take an exam, which is free of charge. It's a certification exam. And if you pass the exam, you get a badge. And it's those badges that you can put on your CV and your resume and your social profile. It's those things that help you get jobs. It proves to your future employer or your current employer that you're advancing your knowledge. So this is all about learning, but it's also about helping you advance your career. So thanks for advancing with us. So before we get on to this week's lesson, I hand over to Isaac. I've got a few announcements for you. I've got them on, I put them on post-it notes across my screen. So I've got quite a few post-it notes on my screen right now. So let me just do a few announcements. First thing is, this is the week where the topic starts to get complicated. Isaac did say that. He's going to tee it up, tell you what he's going to cover today. But I recommend you make sure you've got your favorite beverage. You're really concentrating on this one. Get ready to screenshot because we're getting into some really serious topics about networking. So if you're technically minded, this is good stuff you're going to be enjoying today. And we're also doing something different this week. Me and Isaac had a day out. We went to a secret nuclear bunker, believe it or not. We found something which links the past to the current internet. We're going to take you kind of back in time, into this time capsule of this perfectly preserved secret nuclear bunker, that me and Isaac visited, and we got permission to film, and we filmed inside the communications room at this secret nuclear bunker. It's not in use now, but it's preserved and you can visit it. And we discovered some things. We discovered some things on the wall that directly link to what you're learning about today. It's great. If you like history and you like technology, you're going to love that feature. So stick around until the end to see me and Isaac in the bunker. All right. 2 housekeeping announcements. One is we're coming up for a holiday period for many of us. So this is the last episode before that holiday period. And then the original plan was to restart the lessons on the 6th of January. But we've made a change. We're actually going to go live with episode 4 on the 13th of January, a week later. So when we looked at the schedule, we realized we hadn't really given ourselves enough time to get everything ready for the 6th. So we just pushed it back a week. You're not going to miss out on anything. So if you've got it in your diary for the 6th, then just move that out a week. So episode 4 is going to be on the 13th. We've changed everything on the registration page, so you can go back and double check that if you want. But just in case you've made any offline entries in your diary, then just move the 6th to the 13th. The other thing I wanted to say was follow us on LinkedIn. We've got a LinkedIn profile now. It's we started it off, actually. We called it Extreme Academy. And then a few weeks in, we realized actually there's more things that we wanted to do with that LinkedIn channel. And we've renamed it. We renamed it to Extreme Training. One of the team, maybe Claire, you can put the exact name up on the screen or in the chat window so everybody can find it. And please go and follow us. Please go and follow us on LinkedIn, because that's where we're going to post news. That's where you can engage with us. And we're going to be publishing educational material, content, short videos in that channel every week. So as well as these live streams, we're going to be pushing content into LinkedIn. So follow us on there and you can keep up with the latest hot educational stuff to do with our topic, to do with networking. Got one more thing to say. And we've noticed within the viewing figures for the first couple of weeks that we're seeing a small live audience. So some of you are joining us live, and it's great to see you. Thanks for joining every week. But then we're seeing lots of people watching it on demand, and that's a little bit different to what we saw before. It wasn't as stark as that. So we just wanted to ask you, just if you're watching this on demand, if you're not watching it live, then give us some feedback. Put a comment below somewhere, and just tell us, what's your situation? Are you working and then you're doing some training in your own time, or are you at college and the time doesn't suit? I'll just help us understand the kind of viewing profile, and that may help us do things differently in the future. But we also want to stay engaged with you. If you're watching on demand, then just put a comment in the chat. We can reply there, and use the comment section in YouTube to ask questions as well. If there's anything that you want to ask us, just put it in YouTube in the comments. Okay, that's it from me. I'm going to hand over to Isaac. I can see him. He's ready, and the team are giving me the ready signal. So enjoy this episode. Lots to learn. Look out for the secret nuclear bunker. Over to you, Isaac.
Thank you, Rowan. Thank you, everybody. Hey, guys, thank you so much for watching, for the support, for all the comments, not only on here, on LinkedIn, and for just watching, right? It's so important for us that you watch it, and we really I appreciate the fact that you take 2 hours of your time to sit and watch. Now, not everybody is watching live. People watch on demand as well, and they watch different segments, but really appreciate the time that you take out to do this. Once these videos have been published, Claire goes in and she kindly puts kind of chapter titles in the YouTube videos, so that you can just go and pick up, specific sections, just to make it easier to consume. Right nowadays, we watch so much content that it's like when we're looking for something, it's difficult. So Claire goes in and Claire, you're the best. Thank you so much for setting that up for us. It makes it easier. And all the other Academy courses, course 1, course 2, course 1 was Foundations, to Future Networking. Course 2 was Wireless. If you want to know about wireless networking, access points, that type of stuff, go and watch course 2. Course 3 was just to help you with career. If you want to change job or whatever, how does networking work, what's the language that you would need to have, and it's a bunch of stories from, my favorite was the smart bins. It's a smart dustbins. Yes, smart bins was, it helps you to be able to tell a recruiter stories of how technology can help and do things and change the world. So I hope you've watched that content. Some of this content today that we're going to start getting into, it's what I referred to in the first episode as scary and hairy. Okay, we're starting to get into routing and protocols and routing protocols, and at this point, I don't want your head to explode. Those who know a little bit will find it really interesting. Those who don't know nothing, if the term OSI model doesn't mean anything to you, it might be good for you to go and read, watch course 1. Don't stop watching this one. You keep watching this one, but when it's finished, go and watch course 1. I think episode 1 or 2 talk about the OSI model. I think it's important that you watch that. But otherwise, as we go through, like I say, we start to get deeper and deeper and deeper into networking. But this is important because building scalable, building resilient networks means you build them to achieve business outcomes. So we go for about 50 minutes, 60 minutes, 50, 55, depends if I'm in a talking mood or not, which I normally am. And then we'll have a 10-minute break, and then we'll go for another 15 minutes. So, I've mentioned this before. People say, that's 2 hours is really long. Hey, this is not entertainment. This is not TikTok. They are serious people who come here to learn serious content. So that's where we targeted at. Feel free to interact with us, as Rowan mentioned previously. Feel free, just to answer questions. If you think you know everything, great. Help somebody else who doesn't. That will be fantastic. And then don't forget our Discord channel. Claire, just throw it up. I can't advertise Discord enough. Throw it up. There's a lot of topics today that you might not have the chance to get one-to-one on here, where people can actually help you. Go onto Discord, follow that QR code, scan it, go onto our Discord, and then you'll see there is a course 4 on there. Go ask questions, and there are plenty smart people around, absolutely willing to help and answer. And don't be a troublemaker. Just go there, ask questions, and somebody will help you. Be respectful. Let it be a safe place where other people can ask questions, even 20 times if they don't understand. Help somebody. Be nice. So with all that, let's go. Claire, can you bring up the slide and we'll take it from there. So we've made quite a bit of progress, and we've covered layer 2 side of things. Now, layer 3, for those who are uninitiated, and when they see an L3, they're like, what is he talking about L3? It's not a paper size or anything like that. L3 is part of the OSI model, and it's the part that deals with the layer 3 that deals with routing. Okay, you have local area networks, traffic flows, lovely within the local area network. You don't have any loops, you don't have anything like that. Your MAC addresses are helping you transmit information from one computer to the other, send a document to the printer, send your CCTV to the right location. All of that is being done within layer 2. Very low redundant, very low lag, high performance, everything fantastic. But enterprises are only like that when they are really small businesses operate in a single office. As your business grows, as your school grows, as your hospital grows, you suddenly find you have different campuses. If you're a chain of restaurants, you suddenly find, we've got 20 restaurants within London. We have to run links to all of these. We have to have connections to all. It's no longer local. It's regional. It's multinational. It's across the world: Europe, Asia, Australia, America, Canada, South America. You've got offices everywhere, and you need to route traffic not only to your other offices, but also onto the internet, right? We need to do business with Amazon, and we need to do business with this and with that company, and we need to get access to systems like Extreme Cloud IQ, right? It's not ours, it's somebody else's, and we need to we need to route packets from outside our domain, from inside our network to outside. And for that, we use layer 3 functionality. These are really the building blocks, right? Our devices, physical devices to connect to, like wireless or switches or whatever, a layer 3 switch, servers, these types of things that we need. Routing, layer 3 forwarding switching is needed when packets need to be sent beyond their local network. Now, some people like myself, we say routing. In America, people tell me, no, it's not routing, it's routing. Okay, router, router, tomato, same type of thing. I like to think of a router or router as a traffic officer who directs traffic, in different areas. I've traveled in different places around the world, and sometimes they have a traffic officer on a pedestal and with a whistle, and he's looking at traffic, and it's like, wow, how does he do it? This guy is a router. That's what he does. Layer routing, of course, as we mentioned, operates on layer 3 of the OSI model, and it can generally be performed by any device or different devices that have at least one, but oftentimes more than one physical network card or network port on it. That's very, very important. Routing is a really important function in any connected network. There might be networks today that are not connected to the internet. I mean, I'm sure that there are networks that are not connected to the internet, but you probably find that is, very high level security, military, nuclear, things like that, right? That are not connected to the internet. They still need to get out email and all of those things. But generally speaking, almost every network that needs to connect to the internet is going to need routing to be able to send data. To route successfully, a router okay, a router, a traffic officer needs to know or needs to discover what networks are available to it. And then once it knows which networks are available to it, it then needs to work out, okay, I can go from, think about this, I'm in London, I can go to Cairo, Cape Town, Cape Canaveral, I can go to Argentina, and I can go to Perth, all from London, right? These are all the routes that I can go. But if I want to go to, say, Sydney in Australia, which is the best route to take? This is kind of the job that a router does. It will start to figure out, okay, so how will I get to Sydney? Well, does the plane have enough fuel to fly from London to Sydney? Maybe it does. I don't actually know. Maybe there are other things. Maybe it would say, yes, you can fly there direct, but it will take 30 hours. That means you got a problem, because a pilot is not allowed to be, not fly a plane for 30 hours. You might need to take 2 crews to be able to get you there in one hop. Maybe there are other routes. Maybe you fly from London to Cape Town, and from Cape Town down to Sydney, or from London to Singapore and from Singapore down. Do you understand? When we're talking about routing, when we're talking about routing protocols, when we talk about routers, this is the stuff that we start to deal with. Discovering the routes that connecting to another router, telling me that route, if you connect to that one is connected to X, Y, and Z, understanding that. So discovery process. Then selecting making a route selection. So I have these 3 options available to me. This one is the best. How does it know? They are different protocols. Depending on the protocols that you want, they are different protocols. Have you ever driven or used your GPS to travel somewhere? In the old days, they used to, nowadays they don't do it some more, but you used to be able to choose when it's plotted the route, or before it plots a route to your destination, it used to say, do you want the shortest route or the fastest route? Okay, the shortest route. Is it shortest? I think. Do you want the fastest route, or do you want to avoid, motorways and toll roads and things like that? Oh, I think that's what it. So if the fastest route is on the motorway, but you might have to pay lots of money in road tolls, in taxes to get there. So do you want the shortest, or do you want one that avoids the motorways and all the tolls and things like that? It gives you the choice. That's routing, right? And actually, GPS and all of that stuff that we use every day is really the foundation of the internet, of routing. It's designed by the same guy, and I'll get to that, and it's absolutely fantastic. And then, of course, route verification, to make sure that that is the right place that you need to go to. So let's look at a little bit at some routing overview. If we've got a few minutes, let's go through this. So over here, you'll see we have what we call a SIP, a source IP address. If you remember when we showed you the packet, the Ethernet packet, you had the source IP address, you had the preamble, you had the source, you had the destination, right? So the source IP address, look at this, 192.168.10.125. That's the source IP. But where am I going to? Well, the destination IP address is 30.11. So you can see it's a different network. This is 10.125. This is 30.11. So a router receives a packet and looks at the destination IP address, the layer 3 address, to establish whether it has a path to that destination. So I need to get to a network that's not here, it's different to mine. Where do I go? Go to the router. The router then determines, do I have a path to that particular, to this final destination? And This occurs at layer 3, but no routing is involved at this stage until it's required. So look here, I get there. This is the 10.168 10/24 subnet on this side over here, right? I get to the router, and guess what? The router has an interface that connects to 192.168.30, a 30.0 on a /24. So where do I want to go? Well, I want to go from here to the printer. The printer is on a different subnet. I'm on 10 and the printer is 30.11. The router knows the route to 30.0.24, so it knows how to get there. So from my local subnet, it goes to the router. The router knows, because of a discovery process, what is sitting on this side and is happy to say, no problem. You're coming from this side, the traffic is coming from this side. The traffic officer says, yes, so you can go down this way. Traffic is fine down this way, down you go. That's the job of a router. If the router sees the packet destination, as I've mentioned before, and are different, the destination, whatever is different, it will be processed by the routing engine. So it looks and says, oh, yes, yeah, different, okay, 30, I'll process it. If not, it doesn't need to do that at all. A route is really a path from a particular subnet to a different subnet. That's all it is. Look at this example over here that we're going to be talking about here. 192.168.110.0 on a 24/24. To reach 210 forward to this router over here, So this subnet, right, wants to go to 210. This is the 110. It needs to go to 210. The router says, okay, for that to happen, I need to forward it to 168.12.2. This is 12.2 on the 12.0 subnet. Once it gets here, this router can then forward it on to its destination. So route is a path, and routes inform the router if a network is directly attached. So if on this interface over here, because routers have multiple interfaces, if this network, or if this was directly attached, if this here was directly attached to that, it would say, well, easy, directly attached, that's where I go to. But in this case, it says, no, I know how to get to this router, and this router will know how to get to that destination. Routes tell the routers what and how to get to different places. If a network destination, this is a term you're going to use, if a network destination is reachable through another router, the IP address is something that we call, the IP address of that router is called, is specified as a next hop, not called, but is specified as a next hop. So the next hop from here is that router. Think about a trip, a road trip. You're going from here to Cape Town, from here to Birmingham, from here to Gloucestershire, right? What's the next hop that I get to from here? What's the next town from where I leave in Cambridge? What's the next town? That's the next hop, and then the next hop and the next hop. So if you start thinking like that about hops, if you start thinking about routes as hops, then in your head you can start thinking about things like that we will cover next week. Things like, okay, so there must be protocols that allow me to get from point A to point B, and these protocols, they surely must allow different parameters. For example, maybe do they do something like a GPS? Do they say, do you want to go the shortest path, or do you want to avoid, going through? Do you understand? By starting to talk about shortest path or the next hop, we can start to see that at some point we're going to have options, right? And we might choose, if you go this route, it might take you 6 hops to get to your destination. If we go here, it might take you 4. Which one do you want to go? The router has to make a decision. Routes are fundamental. Routes tell and help routers to determine, even though you have 3 ways to get to your destination, which protocol are you using? What is the decision that it's going to make? Which is the best route to get you there? Which is the best way to go? So I think we've covered quite a lot of stuff. From this point onwards, it really starts going very, very deep. Rowan and I went to a nuclear bunker here in the UK, and we did some filming over there. And I want to show you that piece of that trip, because once you see that, then this whole thing about routing and next hops and shortest paths, when you see that video that we filmed, it for me, it was just like the light came on and I saw it and it was like, wow, this I can use this to explain, because this is so absolutely clear. Okay. You would have heard, I'm pretty sure, if you're into this type of networking, you would have heard of a routing table. Now, routing table is just a database, similar to, like we've discussed previously, with the MAC address table. So this is something else as well. And the router is, or the layer 3 device, just has an internal database that has got a number of different entries on there. There are different types of routes that are held in the routing table. So if a particular route is not in the routing table, that's simply because the router doesn't know about that particular route. Only routes that the router knows about actually make it there. Now, there are principally 2 main types of routes in a routing table. You get your dynamic routes and you get your static routes, right? Now, dynamic routes is really what you would like, because it's in the name, dynamic. As it changes, these routes get updated automatically. Now that's fantastic, but that doesn't mean that's the only type of routes that you're going to have on a layer 3 device, on a router. You do need static routes as well, but those are kind of like the 2 main types. And dynamic route protocols include RIP, okay, RIP version 2, and that doesn't mean rest in peace. That's not what it is. It's routing information protocol. Routing information protocol version 2. Yes, there was a version 1. Version 2 is an update on that. ISIS. IS standing for intermediate system. So intermediate system to intermediate system. OSPF. Open shortest path first, and then BGP. Border control protocol. So these protocols allow routers to exchange their routing table contents automatically. Now, direct routes are routes that are directly connected to the actual router itself, right? So think of it like this. How can I? Let's think about it like this. So, my house is ground floor and first floor. Okay, a direct route would be, for example, if my mum was upstairs and I needed to get hold of her. I don't have to do anything. I just have to go, hey, mum, and she's upstairs. She's directly connected to this house in which I live, in which we have various rooms. An indirect route could be the garage. I have a English say garage. I have a garage which is on the other side of my garden. It's still on this property, but it's on the other side there, and I need to kind of have a connection to that. It's still on my property, it's still part of this, but it's not directly connected to here. Yes? So my direct connection, so for example, my mum upstairs, the direct connection to that is the indirect connection of the next hop router, right? The next hop router, which is that one in the garage, I am the indirect connection, but the direct connection is, for example, upstairs to my mom. Does that kind of make sense? So let's look also at the following. You get dynamic routes, static routes, direct routes, indirect routes, and you get default routes. So the way I like to think about default routes is that's the gateway to get you to a network that doesn't exist within your area, your autonomous system. So think of it like that. Think of it almost as a catch-all, a safety net. In other words, if you need to communicate to another computer and it just so happens that that computer cannot be reached through all the routes that you have within your enterprise, well, if it doesn't know about it, then it needs to go to that particular router to get out. Sometimes we call that a gateway, or most times it's the internet gateway. Look at this over here. Here is the default route. In other words, if you don't have any specific route, then this is the place, this is the next hop that you will go for. That would be the gateway, and that gateway would get you out onto the internet. Make sense? Yeah. So these are all, here you can see all the different routes. Okay, subnet masks, and this is the next hop that you would go. So it could be the router's address. That's where you would go. So to get to that network, you go to this particular router, this particular interface. So static routes. Let's talk about. We've spoken about this. Let's talk about static routes. So, like we said, we like dynamic routes because that's their nature. They change as things change. So we like that. But a static route is something that you would set up manually. You as a network administrator would set it up manually, and it could be for a very specific purpose, right? Certain network, you only want that to connect to there, but you don't want it to be discovered by routing protocols. You want to set it up yourself for a particular way, for a particular reason. You can go and set up a static route. Right, so let's look at the routing table, and let's see how a routing table makes decisions, because we've looked at, previously at the choice of routing protocols that we have, and we've said each one will have characteristics, different characteristics that make them appropriate or not appropriate for certain tasks. But let's take a look at something like this. We're kind of aware already of the source IP and destination IP, written as SIP, SIP, and DIP. SIP, source IP address. We saw that when we spoke about Ethernet. The frame, every letter has to have an address, a destination IP, a destination address on it, and on the back you normally write the source IP address. So we kind of know what it is. So here we have the source IP address, which is 192.168.10.125. That's the source IP address. And where do we want to go? we want to go to the same network, 192.168, but 30.11. All right, so that's not within our little segment. That's maybe not within my house. Maybe that's in the garage. There's a router over there, and that's where that address is sitting behind that router. So a routing table that's sitting on a router, by the way, this is kind of the illustration, the universal illustration or diagram for a router, which has got the icons pointing inwards and outwards. Now everybody has their own version. Here is just a round one. You get square ones, you get whatever. The important thing is those arrows, they define that this is an actual router. So you'll see this in a lot of documentation, a lot of presentation, stuff like that. That's the symbol, the universal symbol. So let's look at this table. And then we have the destination and the next hop. Remember I showed you the default route. So the default route over here says, if I have no idea, if I have no idea, does that? Okay. If I have no idea where this route actually is, or where this computer wants to go, I have no knowledge of that IP address within my domain, within my area, my autonomous system. If I don't know, then go to the gateway, go to the internet gateway. That's going to get me out onto the internet, and that you always got to have over there. But like we've said, a router might have routes, and for you to get to destination A, there might be multiple paths to get there. To use the example or the analogy of me living in Cambridge, wanting to go to London, well, I've got the M25 that runs all the way around London. So I have various ways to reach the M25. And then when I get there, I have various ways to go. I can go one way, or I can go clockwise, or I can go anti-clockwise, right? Both those paths take me to where I want to go. But now I need to determine which of those is preferable. And I might, in my head, have various various preferences. For example, if the GPS were to say to me, would you prefer the fastest route? Would you prefer the shortest route? If I had toll roads on the way, would you prefer to go that and pay a toll? Would you prefer the one that's going to save you the most fuel? If it presented those choices, then I would have a choice where I want to go. Maybe it would say, well, this is the shortest, but it's going to have more traffic. It's going to take you longer. And routing is kind of the same thing, right? I want to go from this network to that network. Okay, well, I've got a couple of choices. How does a router make the decision where to send you to? Well, it has to do it through a list, a prioritization list. Without that would be really crazy. One day it could send you this way, another way that way, another day that way, send you, and that could change all the time. If you think about it like this, let's say you live wherever you live and you have a supermarket, that your preferred supermarket. In other words, you always go to that supermarket. Or let's say you have an office and every day you drive to your, nowadays that doesn't work so well, but you drive to your office every day. You already know the path that you take with your eyes closed. But if you put that into the GPS every day, in the morning, every day, you say, I want to go to that destination, the same destination. Chances are that the GPS almost every single time is going to send you on the same route. Okay, I say almost because sometimes it might be aware of something that has happened on the road. It might be aware of an accident or whatever. For example, if you turned off your mobile data on your phone and it needed to make a decision, well, it would always choose the same route because it's going to figure out, well, I have 3 routes to get to work, but this one is 15 miles and the next closest one is 45 miles. I'm always going to send you here. It's just the fact that we are able to get data from other cars that's sitting in traffic that helps us to get a faster route when there are issues. But in general, a GPS will always send you to that supermarket or to your job using the same route. And generally speaking, routers will probably send you down the same path more often than not if things stay the same, if things don't change dramatically. So they achieve this by having a prioritization of how they get you to your destination. And the first one that it uses is the longest prefix match. So let me show you here. Here's the destination, the 30.11, and it says the longest prefix. So let's take this first part here, 192. Do I have in my table, do I have anything with 192? Yes, I do. I have that one, I have that one, I have that one, I have that one. So I've got 1, 2, 3, 4, 5. I've got 5 possible routes that it could take. Okay, I can't take 5, I need to take 1. So if it says the longest prefix, let's go to the next piece, 168. Oh, that's okay. Oh, I also have one there. I have one there. Ooh, I'm still sitting with 5. Okay, let's go to the next one. Let's go. We've done 198. Let's go to that third piece over there, 30. Well, I got, oh, no, 0. No, not that doesn't match. That doesn't match. That doesn't, oh, that one matches. What about this one? That doesn't match. So this one matched on 2. That one matched on 2, on 2, on 2. This one matched on 3. Do you see that? Bingo. The longest prefix match. Now, of course, if the longest prefix match, if you had 2 routes that match that, then it will if all routes match the destination, the direct route is preferred. So if all of them match the destination, then it would say, well, do I have a direct route? Well, this one happens to be a direct route back, so I'll prefer that one, and boom, that's where I go. Then I'll have, if none of them can produce a winner, then I'll go to a static route. If there's a static route, that's what I'll go and look at, and then dynamic routes. So you can see that with this order, with this particular prioritization order, it becomes pretty easy for the router, when given choice, to make a decision which is the one that is going to be that I'm going to be sending me to. It also doesn't necessarily mean that it will always send there, right? Because if your network is very static, if you don't have changes on your network, if you don't have new routers being added all the time, if your network hasn't changed in 20 years, well, that's not going to then affect this much. Generally the same place all the time. But just like in a road system, they add new roads, they close one, they open this, they widen the lanes over here, they add more highways here, the freeway there. And by doing all of those things, the routers change. You add more routers, more roads, and then your GPS might calculate and find a better route. So although it can be always send you to the same place, if you have a dynamic network, that could change much more often. It completely makes sense. So now that we know, what the routing table is and the different routes, now we start to go a little bit deeper still, and that's when we start thinking about protocols. Remember, we said protocols sit on top of Ethernet, and they help, enhance maybe the deficiencies of Ethernet, and they really are incredibly useful. So now, if we are building a scalable network, if we are building a resilient network, we have a choice of routing protocols that we can use. But what is it that's going to actually determine which protocol we use? Well, look at some of the protocol characteristics that we have. The type of algorithm. That's, the algorithm that it uses. That can be a little bit mathematical, and not everybody's going to understand that, but certainly speed of convergence is important. Now, what do I mean by convergence? And I think it's coming up in another slide. So, but basically the speed of convergence means if something changes, how long does it take before everyone is aware of the change? Let me give you an example. A couple of weeks ago on the road, outside my house, on runs in front of a school and a hospital, they did some roadworks on there. But because it was a school, there's kids walking around and all sorts of stuff, they actually blocked off the road. So only residents who lived, in this area could actually come into the road. Otherwise, you weren't allowed to do that. But there was no convergence into a GPS system. So if I was in central Cambridge and I wanted to come home and I put in my address, it didn't show that there were roadworks at the time. Now, some of them are good. Like if you use Waze, it's pretty good because it's driven by people who go and do updates. But if you use one of the other ones, it doesn't always update that quickly. So the convergence is slow. If those roadworks had been there for maybe 2 months or 3 months, maybe that would have manifested itself in the GPS. In networks, you can't wait 2 or 3 months. You can't wait a day. You can't even wait hours. If a network changes, if a router goes down or you add something, it needs to converge as quickly as possible so that everybody knows, hey, something new has happened. The road has been blocked, or the road is open. It's now working, or we can carry more traffic. We have more lanes, more bandwidth. Does that make sense? I hope so. I know those are kind of big words, and sometimes we just assume everybody knows. And if you know, I apologize. But if you don't, great. You've just learned a new word, right? Convergence. And then, of course, scalability. This is what some of these protocols have. Some are more scalable than others. Doesn't mean that they are not scalable, just more scalable than others, right? So you might have scalability, the ability to grow without affecting performance. That's really what we're talking about. The ability to grow without negatively affecting performance. So that determines, these characteristics here are going to help you determine which routing or routing protocol you're going to be using. Now, let's look at what the input requirements would be to determine, so that to get you to a place where you can determine which is the best routing protocol for you. Well, first one, the size of the network. It's obvious. A network with, 150,000 points on it, 150,000 users or computers or devices, the routing protocol you're going to use for that is going to be very different to one that you're going to use in a computer in a company with 10 people, right? I mean, it just makes absolute sense. So size is going to be a determining factor. What about multi-vendor support? Nowadays, almost everybody that's in a business that wants to build a business for outcomes, wants to grow, wants to do all of that, they are pretty resistant to proprietary protocols, right? Because the minute you tie into a proprietary protocol, that means you tied into that company. And if they charge tons of money more, you don't have a choice. You tied into there because their equipment doesn't talk to anybody else. And nowadays we like open standards so that if I use A brand or C brand or D brand or whatever, they will all work and they will all be able to communicate. So generally, multi-vendor support is like, if you don't have it, forget it. I'm not going to go that way. What about knowledge level of a specific protocol? Listen, protocols can be extremely complex, okay? To fry an egg is really simple, but to make Julia Child's recipe for boeuf bourguignon, not so simple, right? You need a lot of time and you need to do a lot of steps to be able to do. I don't think I've pronounced boeuf bourguignon. Oh, I'm sorry to the French speaking people, but you get my point. My point over here is that if you need a PhD to understand a protocol, that's maybe not a good idea, right? It might be great, but nobody can fix it until you get a PhD that charges you, £5,000, per half hour or something like that. Get the message? Yeah. Okay. And then what are factors that you could consider as well is something like, let me just bring this up here, a number of routes. The number of routes. If think about an organization like Walmart in the US, they have, I'm sure it's thousands, if not tens of thousands of branches in the States. Now, think about, trying to put some of these protocols on switches that are maybe not powerful, or routers that are maybe not powerful, cheap stuff. You might find that although it could run it, it places a really heavy load on that particular switch. So that might determine, why you would choose one protocol over another. It makes complete sense. The number of adjacent routers. So in my house, that example, I have one here and I have another router, just one next door. That's great. That's my adjacent. That's my neighbor. All good. But I'm a house. I'm nothing. An enterprise could have hundreds of neighbors. Again, is this a big issue or not? You might have an enterprise with 500 people, and you might only have 2 routers across those 500 people. So the number of routers and adjacent members or neighbors is important as well when you need to consider which protocol you're going to be choosing. Network design, the frequency of changes. Some organizations, by their very nature, are quite slow or are quite static in the growth. They reach a certain, maybe for example, a charity, a fundraiser or something. You don't imagine them changing every day and growing and adding routers and all of those things. You probably find that there are many businesses that grow very quickly, that expand very quickly, and it's very different. If you think about Google, surely Google is constantly growing and adding routers onto their networks. Netflix must be the same kind of organization, always growing, always expanding. Well, if you are that type of organization, then you can see that any protocol that takes long to converge, it's just not going to work for you, right? You can't afford that if you're a Netflix for it to take, 30 minutes to converge and replicate all the data. So design is important, how you design your network, but part of that design process is understanding routing protocols. And part of choosing that is understanding what are the parameters and what is important to your business and the business outcomes of what you're trying to achieve. And then, of course, the actual devices, the router themselves, the layer 3 switches, those things are also important because you need processing power. You need CPU power to be able to handle all of these things if that is what you want to do. And if it's a very dynamic organization and with a lot of changes constantly growing, using, 10-year-old technology is just not going to cut it for you. It's not powerful enough to handle everything that you need to do. So I said we're going to talk about convergence, this nice word that we've kind of understood. If you take a look at this diagram over here, 2 headquarters, headquarter A, headquarter B, and we have 3 branches, A, B, and C. Now, overall, it looks like, yeah, that's okay. With that type of a solution, you could just, if you just look at it visually, you could say, well, that works well. I mean, from headquarter A, I can reach anywhere, and from headquarter B, I can reach anywhere, right? Does that look like a good network topology design to you? Come on, go and put it in, just say yes, no, yes, no, yes, no. I'll leave a few of those waiting. Oh, come on, you guys are so slow. Convergence is when every router in the network is carrying the same network, the same view of the topology, okay? When every router on your network is carrying the same view, sees the same thing, okay? Some of you said, yes, it's a good design. Others said, no, it's not a good design. Whether it's good or not, I'm not sure. If I was designing for resiliency, I don't think it would be a good network for me, because look what happens if that link goes down. Okay? If that link disappears, what suddenly happens? Is this a converged network? No, it's not converged. Why? Because look, this one and this one need to now converge, right? Because something has changed on the network. A change has been detected. They now need to converge, and they will converge, and these guys will also converge. But the routing tables on both of these are not going to be the same. This one, this over here, has no idea of that because the links are down. Okay, the links are down. So it has to have a different, this is a non-converged network. So convergence is the normal and the desired state of any network. And it's achieved when all these routers exchange information about the topology and all of them is the same. Boom, then it's done. When there is a, when there is a change that happens, they need to replicate the change. And that convergence time needs to be very small, or as small as possible. That's a decision, right? That you need to take. So that's one thing, convergence. Another thing that is really useful for networks and for network designers is something we call route summarization. And I kind of think that this slide actually shows exactly what this is all about. But in this slide, if you take a look, and by the way, screenshot it because this is a good one to do, you'll see you have two routers, router A and router B. And on the left-hand side, you can see that router A has a whole host. I think there's 8. 1, 2, 3, 4, 5, 6, 7, 8. It's got 8 subnets, okay? 8 subnets that are in this routing table on router A. Now, that works. I mean, 8 subnets, but think about it. If one of these subnets is suddenly out of commission, what happens? Well, this one would have to trigger an update, and have to, notify this router here that there's been a change, and then they're going to have to converge, take a little bit of time, converge, this is no longer there, and that kind of makes sense. We understand that. But what if you could aggregate all of those and fold those in to a different network, right? Have a summarize all of these into something else. And we can do that. Look at this. 10, 12, 10, 12, and then 0, 0 means all all of these. So what we can do here is we can take these 8 individual routes and we can summarize them with simply one. So let's go back to this example. If this one here, if that one goes offline, if that one, starts to feel, too high a blood pressure and goes offline, so what? It does not trigger an update because the summarized route, the summarized entry covers all of those. So in large networks, small networks, it's not that much of a deal, but in really large networks, there's 8 entries here. You could have thousands of entries in a route table. If you manage to summarize routes in your routers, it means that the amount of traffic that goes out on your network that needs to update and keep all the topology, updated, it means that is reduced. The amount of traffic is reduced. The amount of processing power is reduced. Imagine if I had 200 routes and I could reduce it to 4. Can you imagine the factor of summarization that doing something like this, the effect that will have on my hardware, on my traffic, on my network traffic, all of those things. So I think you get it. Route summarization, smaller routing table, fewer updates, improved conversion times. That's just like, a bonus win for no money, for no outlay. Okay, so now that we've kind of know what effects routing has and routing tables and these things, and we know that there are different decisions that would lead you to choose a particular protocol, etc., etc., etc. What are the metrics that routers actually use? Okay, what are the metrics? What are the determining factors? Well, let's go back to the analogy of traffic, right? I want to go to London. That's the route that I'm in Cambridge and I want to go down to London. Which path do I take? Okay, I ask the GPS. The GPS is going to calculate and see, there's 12 paths that it's going to take. And generally, it's going to pick the fastest one. That's one thing I've noticed. It's oftentimes the fastest one, not the shortest one. Okay, so in terms of distance, so it might see one and says, that's 80 miles, but that's going to actually take you an hour and a half to get there. This one is 110 miles, but it's going to take you, just an hour, just over an hour to get there. Okay, so it kind of makes that decision. But for a router, what are the metrics? And these are the metrics over here. Bandwidth, that's a consideration. Delay, what are the delays, the ping times, for example, the response times? What about the cost? Now, generally speaking, a cost is not money, that we're talking about. It's not a monetary value. I guess it's not impossible to be, but why would you do it as a monetary value? But it could be an arbitrary cost that you could put on there. When you design CDNs, for example, you might say, I'm in London and I'm going to have a backup office or backup servers in Scotland and in Ireland. And I might say, okay, if my servers in London go down, then I want you to go to Ireland first instead of Scotland. For that to happen, I would have to give it a metric and say, my cost from London to Ireland is, say, 40, but my cost from London to Scotland is, say, 60. So by choice, if my servers go down, I will reroute you based on a cost. And that cost is, like I say, it's an arbitrary cost, like a manual cost that you would put in there and say, first Ireland. And then if that's not available, then go to Scotland. Kind of a prioritization. So that's cost. What about reliability? That might be another factor for you. Hop count, right? The kid on the street who draws on chalk, little squares, and then they hop, the boys or girls or whatever, they hop, how many hops to get to your destination. You might consider the hops as very important. So I want to get there within 3 hops instead of within 20 hops. So, and any path attributes that you might get along the way. So these are, generally speaking, a category of metrics that routers are going to use when given a choice, when given a destination, and they come up with a whole lot of different options. The metrics are going to help them to decide. So let's look at this example that we have on screen. So for the next few minutes, I'm just going to be looking down over here and seeing what we're going to do. Let's take this example from a point of view of bandwidth. Okay. So here's Isaac over here. He's got his computer over here, and he wants to get to here, right? He wants to get to somewhere else, wherever that might be. Okay, so he comes in to router 1, okay, and now look, if I'm going to use bandwidth as the metric, then I've got 2 choices, right? I can go this way or I can go this way. Both of them give me the same because bandwidth, they both got 1 gigabit per second. Okay, so if I go down here, if I go down this route, I end up on this router here. Okay, that one. Let's just mark that one. Okay, once I am here, I have got a number of choices, right? I can go up this way. This is 100 meg. I can go 1 gigabit that way. I can go 10 gigabits this way. Wow. Okay. So let's concentrate on the bottom one if I chose that path. So that means, okay, so if it's bandwidth related, definitely this is going to be the next one that I get to, my next hop. Okay. But now that I'm here, I actually don't have a choice. Now that I'm here, I don't have a choice. Where's the next hop? Well, I have to go here. Now I land on this router, and now remember my destination is here, right? That's where I want to go. So from here, how do I get there? Well, I could go this way at 1 gig. I could go this way at 1 gig. They are both the same. If I choose this way, I'm immediately there. If I choose this way, right, and it might make a choice. It might make a choice. It's now on bandwidth that says, well, both of these are the same. I'm going to use cost. Is there a cost on there? Did the customer put a cost on the network? If there is, let's say the cost here is 10 and the cost, let's say here is 5. Well, if that was the case, then 1 gig, well, I'd go to that cost because it's the next hop, and then I'd go across to there. So how many hops in total? 1, 2, 3, 4 to there, 5 hops. Okay, it works. But what if I had chosen this one? Okay, and let's say that they had equal costs on them. Well, maybe I could have gone for, I don't know, for path attributes. I'm not sure. But if I had gone this route up here, that would be 1 hop to this guy, to that router. Now that guy says, okay, I could go 10 gigs right to this guy here, or I could go 1 gig to there. Well, if it's bandwidth, then I would hop to there. That's the second hop. From here, I can go 1 or 1. Okay, I might go to there, right? So you would then have 1 hop, 2 hops, 3 hops. Okay, so that would possibly be a learned route. Say, here's the choice. This is the way that I'm gonna that I'm going to go. So metrics are what routers are going to use, and they might use more than one metric to be able to make a decision as to how they get to an actual destination. Okay, and there's going to be different protocols. For example, the RIP protocol, the RIP v2, so not rest in peace, routing information protocol v2, that is going to use hop counts. So that would be the metric, the hop counts. EIGRP is another one that uses bandwidth and delay. OSPF, that uses cost related to bandwidth. IS, cost manually associated by an administrator. So you as an administrator would go and say, this is the cost, that's the cost, that's the cost, that's the cost. So that protocol would use that. And then BGP, that uses path attributes. So we'll break at this point in time, and then we're going to break for the 10-minute break at this point in time, and we'll come back afterwards and continue on from here. Cheers.
Hello and welcome to Megatrends. I'm John Barger. Each week we'll be walking you through the biggest megatrends in the industry and what you as a job seeker need to know about them. Those megatrends are working from home, mobility, as a service, as well as artificial intelligence and machine learning. As we go through each of these, you'll see how they're interconnected and interdependent. But before we get started, let's find out what some extreme employees feel about this week's megatrend.
Clouds is clouds or clouds is clouds?
Whatever you think a cloud is.
A cumulus is a cloud.
Cumulus clouds.
Well, I'm sticking with cumulus nimbus.
Cumulonimbus.
Obviously, we're going to start with extreme cloud, extreme cloud IQ.
We've got our XIQ.
You could say AWS, Google, Extreme,
AWS.
Amazon AWS is a cloud.
Azure,
Google Cloud Platform.
Apple has a cloud. You've got iCloud.
The ones that block out the sun.
A bunch of smoke floating around, which is also a cloud.
That's a tricky one, that is.
Today on Megatrends, we'll be talking about as a service. Megatrends are aspects to life, work, or communication that have rapid and wide impact. As a service is practically a stealth mode megatrend that's been impacting your life for years. As a service is the process of offloading the hosting and maintenance of a personal or business function to a third-party cloud-based service. Sounds confusing, doesn't it? It's really not. There are many types of cloud-based services. The most common is software as a service, or SaaS. This could be an accounting system, an HR record-keeping system, a network management system, or any number of other types of software. There's also data as a service, compute as a service, infrastructure as a service, and so many more. But again, the most common use case that you'll run into is software as a service. It may surprise you to find out that you've been using as a service for a very long time. When was the last time you rented a DVD or Blu-ray? When was the last time you sat down at the kitchen table to fill out paper checks to pay your bills and then mailed them out? Physical mail with stamps. Depending on your age, you may have never done either of these things. For most of the rest of us, it's been 10 years or more. Now we just flip to Netflix, Hulu, or some other streaming service. Almost any movie or TV show is at our fingertips with virtually no effort. Not only that, but we can access them at any time, anywhere, on almost any device. Many of our bills are paid automatically, and the rest are taken care of with just a few taps on our phone. Look at how you're consuming this training course. You're not commuting to school, trying to get to classroom on time. You're not listening to in-person instructions. You're learning at your own pace in the way that works best for you. As a service is all about flexibility. And when it's done right, it reduces cost, time, and stress. Let's look at a few more examples. Do you have security cameras at home? Are they wired to a video recorder, or do they send their video feeds to a cloud service like Ring or Nest? Do you back up your phone to a computer, or does it automatically get backed up to a cloud service like iCloud or Google Drive? Now, most of you will have answered cloud, but some people choose the other option. Why? It's obviously easier and more resilient to use that cloud service. Those services also continually add new features that improve the experience and usefulness of that service. This is rarely true for self-hosted systems. While many people like to control every aspect of their experience, maybe they want to record the video in a specific resolution or format. Perhaps they want to tune the night vision capabilities of the camera. Or maybe they have security concerns. Security camera footage might contain sensitive content, especially if those cameras are inside. Your phone contains passwords, pictures, and other content that you might not want falling into the wrong hands. How do you know you can trust the company that runs this service? What about their disgruntled or dishonest employees? While many aspects of IT have already moved to as a service, some IT professionals are hesitant for similar reasons. They might want to control every aspect of their infrastructure. This means that they are willing to put in much more effort and take more risk to keep all of their systems in an environment that they control and pay for. In many ways, this is old school thinking. Many enterprise as a service offerings give you nearly the same level of control as a self-hosted system. In some cases, they can give you even more control. Security is a valid concern, and here I am not going to downplay it. Security should be of the highest priority to any IT professional. If it's not, they won't be in their role for very long. That being said, cloud-based services can be just as secure, if not more secure, than any self-hosted platform. But you need to do your homework. Be sure that the cloud service that you partner with runs regular third-party audits and maintains industry-recognized security certifications. If they don't, ask them why. I would be very hesitant to trust my valuable corporate assets to such a service. As you progress in your learning journey and your career, keep an eye out for aspects of your personal and professional life that seem antiquated, slow, or cumbersome. Are these areas that could benefit from a cloud-based service? How would you make that move happen? Moving to as a service can be a hard decision for many IT leaders. It's a good thing they have you and me to help them get there. I hope you found this edition of Megatrends helpful and are enjoying your journey into IT with Extreme Academy Live. Thank you.
Okay, welcome back from the break. This is where we were when we ended. So let's go to the next one. Based on how protocols operate, they can be divided into three main categories. I'm going to read some stuff on here, but of course I'll be talking and teaching. This is not death by PowerPoint. That's certainly not what we want to do over here. But you have distance vector protocols. Screenshot this. Distance vector protocols, link state protocols, and path vector protocols. Okay, so the protocols that are used for routing broadly fit into kind of these three sections. Now, on the first one, distance vector protocols, think of it like this. Think of it as the routers are signposts, signposts. And all they know is they just know where that signpost is. So all they know is like the vectors, the direction and the distance to that next signpost. They don't have a topology map. They don't have a map of the entire network, the entire country. They don't have an atlas map. Yes, they just know, there's a router there. It's 20 away from me, a cost of 20 or whatever it is, and it's in this direction, in this vector. Okay, it knows how many hops to get there. That's all that it knows. We call that sometimes routing by rumor, and you'll see why in the next slide when we go into the next slide. It's not really recommended for enterprise autonomous systems, and a protocol that is common, a distance vector protocol would be routing information protocol V2, generally V2, routing information protocol V2. The link state protocols are, they exchange, that a family of protocols that exchange accurate link state. Now, link being the interface, okay, the interface, and the state, the relationship to an immediate neighbor, okay? So they exchange accurate information. This is much more accurate than distance vector protocols, although this particular one does need more grant, more processing power. To be able, more memory, more processing power to do. And each router determines the best path using the shortest path first algorithm. Okay, shorting path first algorithm. A big advantage of this is that it has, of all the three, it has the fastest convergence time. So the reason for this is that it doesn't really need signposts. Excuse me, I should have had this. It doesn't really, if you think about that analogy of the signposts, where the first one just knew that, the signpost, the distance, and the vector, this one doesn't need signposts because this one has a topology map of the entire network. So each router has a topology map about the whole network, and it knows all the links to everywhere on that topology map, right? It's just like an atlas. You open up an atlas and it's got all the routes from everywhere to everywhere. It's really quite easy. So this has got the fastest conversion. When there are changes, when you take one down, you bring one up, you add a new one. When you do that, that conversion is the fastest out of all of these three categories. It's also the best autonomous system choice. Now, autonomous system, AS, I've covered that already, but it's a generally, you could say, maybe I can describe it like this. An autonomous system is a network. Yeah, you could say a network or network of networks managed by a single technical entity. I think that's a pretty good description. A network or networks managed by a single technical entity. So if I go back to my example of Vodafone, and I'm just using Vodafone because they come to mind, they ultimately, they might have, in the UK, they might have different branches, more than one headquarters in all the countries within the UK, and they have, regions and all of that. But ultimately, there's probably one guy, a CTO at Vodafone, one guy, technical guy, that heads up the management of that entire network. Okay, so that's what we mean by autonomous system. That autonomous system. So the best autonomous system choices. So Vodafone UK, Vodafone France, Vodafone Spain, Vodafone Portugal. This would probably be the real best routing protocol for something like that. Certainly the fastest for convergence and so. And the protocols there are the OSPF and ISIS. We'll cover what they actually mean. The third category is what we call the path vector protocol. So they exchange routes as the vector of path and direction. The path would be a complex list of different path attributes, and the direction would be, well, the direction of the next hop neighbor. This is the most scalable. It's also very good, like the link state protocols, very good for inter-autonomous systems for connecting those. And then it uses BGP. Now, it's important to note, for example, that you might have an organization, an enterprise, that doesn't have the same ISP, right? So, or no, I don't mean that. So you could have an organization, let's say, again, Vodafone or whatever it might be, or let's take Extreme. Extreme might have an ISP here in the UK in Reading, and they might have another totally different ISP. They would in Salem, New Hampshire, in America, and another one in California. At the other offices in California. Okay, so that's three big offices. Chances are that they would have different ISPs on all of those, probably, right? And those ISPs could themselves be using different routing protocols. In cases like that, to connect all of those, you would probably use something like, they would all be familiar with BGP. So even though they might use different routing protocols internally within their autonomous systems, ultimately when they talk to someone else, they would use something like BGP. So they could all use different internal routing protocols, but connect all of these organizations together just using a common protocol like BGP, Border Gateway Protocol. Now let's look at distance vector routing. Distance vector routing. What's that about? Well, we want to know how far, and we want to know in which direction. That's what we particularly want to know. And so, on occasion, the routers, they pass periodically, they pass copies of the routing table to the neighbor. Okay, and then it accumulates. They start accumulating knowledge that they're getting from their neighbor all the time, and that's what we sometimes mean by routing by rumor, because they might not necessarily have all the latest information, but they pass what they have. So if they've been busy with an update, a partial update, they just pass that along, and the next one gets that, and the next one gets that, and so. That's the mechanism that they use to keep themselves informed with all the dangers that it apply, by rumor. An example of link state routing is OSPF or ISIS, and in this case, it's more accurate and scalable when compared to distance vector methods. They simply exchange information about the links and their relationship to neighborhood routers. More memory and processing power is required. So what that means is they have this topological database. And after the initial flood, after you set up everything, there's a lot of information that gets exchanged between all of these routers. But once that has happened, if there are any little changes to it, then it's just that little change, that's added. So because they have a topological map of the whole network, they only need to change one little thing. They don't have to go in and change everything on this. Okay. So very easy to understand. It's one big one initially, and then after that, just small little changes that happen. Of course, they need more memory than the other one, because they need the memory to keep all the topological map, to keep the whole thing. Remember, the other one just kept really, in an analogy way, it just kept a signpost. It just needed to know the signpost of and the vector, the direction of the next hop. These have full topological maps. Open shortest path first. This is an interesting one. This was kind of developed around 1987, more or less. So it's been around for a long time, and that has to be in a tribute to how good it is. So routers communicate information using think of it as an advertisement, right? You watch a program on TV, every 5 minutes there's an advertisement. So they call that link state advertisements, LSAs. So that's kind of the thing. Whenever there's a little change, they make this announcement, this advertisement. They put out this advertisement all the time. So the shortest path between networks are chosen based on point-to-point cost, point-to-point cost. So that's been one of the metrics, and they really are based on this. So okay, let's go to open shortest path first. The O stands for open. Okay. Open as not proprietary. This doesn't belong to any individual company or so. It is open. That's what the O in the OSPF. And then SPF is shortest. Okay, shortest path first. Okay, so I think the name kind of really explains it. It's really easy. I'm here at point A in Cambridge. I need to go to London. I have this path, that path, that path, that path. Okay. I have my vectors. My metrics is distance. Okay. So distance, this is 80, that's 100, that's 120, that's 72. Okay. Shortest path, that's the one that I'm going to go. That's the one that I'm going to take. So that particular algorithm was invented by a Dutch scientist called Edgar Dijkstra. I'll write that on screen. Dijkstra. Dijkstra. I hope I pronounce that correctly. Dijkstra. Yeah, Dijkstra. So Edgar Dijkstra. So what he wanted to do, and he was around the 1956, somewhere around there. He had an issue, right? If you and I want to get to a supermarket, then it's really easy for us. Yeah, it's really easy for us because we know in our heads, okay, that's the path that I take. It's easy. But if you wanted to describe that mathematically, how would you do it? And so Dijkstra's algorithm was an attempt, or his attempt, successful attempt, to describe the path using a mathematical formula. And Dijkstra today, it's his formulas are used in absolutely everything that you can imagine, from GPS to routing and anything in between. Open shortest path first, or shortest path first, is based on that. So thank goodness for Dijkstra. Very often used within the boundaries of enterprise, within enterprise networks. Oh, I shouldn't have written there. Oh dear. Let's go here and let's say let's just clear that. All right, Shift E, I need to remember that. All OSPF routers maintain identical topology information database, and a routing table is derived from that topology. Again, very quick recalculation when there are changes. So the convergence is really, really quick. So OSPF uses the concept of a hierarchical structure. Hierarchical structures are great because they scale up very, very well. Just think of DNS, for example. DNS is a hierarchical structure, and look how well it scales. So the OSPF system, in a small network, it's really easy, right? It's easily determined, the best part. But the information to describe really large networks can become really complex. SPF calculations turn into really time consuming. Think about a road. I want to get to London. Think about how many calculations and how many roads need to be looked at to come out with a path. Now, iPhones are incredibly powerful, and Android phones and everything, and you press, and a couple of seconds later you have an answer. Of course, Dijkstra's theorems have been improved, and nowadays they lay all sorts of things like traffic and all of that on top of those that make them so much more useful. But you can see how in very complex networks these things can become memory and CPU intensive. So how do you kind of resolve that? Well, OSPF uses a two-level hierarchy, right? One is called a backbone transit area. You can see that over here, a backbone transit area, or area 0, if you want to call it that. And the others are just called non-backbone areas. Okay, so you have this, the backbone, and then you have these. And of course, for a backbone to be a backbone, it's got to be able to connect to all the other non-backbone areas. That's quite logical. And the backbone will also then connect to an external routing domain. Now, in area 2, for example, or in area 1, you could have huge amount of routers. In fact, actually, it's recommended that you don't have more than 50 routers within a particular area. Now, that's already, 50 routers is a big network, right? So you have different areas. Now, imagine if each one of those 50 routers, and you had, say, 10 areas, that's 500 routers. Imagine if they were all sending their information through. That would be really, really heavy. So what you have is you have this concept of a ABR, which in, let me just see, oh man, I remember that, what ABR, an area border router. And so instead of all of these routers, these 50 routers sending out notifications about the routes, this one is the only one that communicates with the area backbone. So when things change on it notifies the area backbone, and then the area backbone knows how to connect to this one over here, and then this one is completely aware of all of these 50, up till 50 routers over here, and between them they exchange the routing information. But that routing information doesn't go everywhere else, just from here. So it's kind of this hierarchical structure that you have, and all traffic from area 2, if it needs to go to area 1, they all go through the backbone. Everything goes through the backbone. The other thing to remember is generally in this backbone area, you don't have any users. So there's no users there. That's just hardware infrastructure. So from area 1 to from area 2 to area 1, you don't go this way, you go through that area backbone. That's kind of OSPF. Now, how does it work within, those particular areas? How do they actually work? Well, there's something called a hello packet. So think about you moving to a new neighbor, into a new neighborhood. You move in, you see your neighbor, hello, you kind of exchange, you exchange niceties. Nice to meet you. Now, yeah, come over for a cup of tea. Yeah, because that's what we do in the UK. We have tea and cake, right? And you kind of do that. So you use hello packet exchange to discover the adjacent routers that are next to you. So that would be the first step, discovering those particular routers. The next thing that you do then is you use that LSA exchange to update the databases on each one of those routers. LSA being the link state advertisement. Remember those adverts? Well, you use link state advertisements to update the databases so that all these databases have current information about the neighbors, about the adjacencies, about all of that. And in the end, what that does for you is it creates this topological map where the shortest path first route calculations are done. And so everywhere it knows how to get to the next one, it knows all of that that information. That's really clever, and it just takes the load, of all of this, because it's this hierarchical structure. So you tell me about this, you tell me about that, everybody tells me about this. I now know this. I exchange some information with the other guys, and now we know how to reach each other. But once we reach there, we can reach any other network. So that's really that's really quite clever. Now, am I giving you the all in all of this? Oh, I wish. OSPF, I've read, I've studied, I've spent a lot of time with OSPF, with SPF as well. You know what? These protocols can get so complicated. They can get so deep on here. I met a guy once who worked for Bell Labs. Right now, Bell Labs is like the creme de la creme of engineers, and he was a networking engineer specifically. And I went out, I took him to dinner in Cambridge, and we were chatting around. And I said to him, tell me about BGP. And he kind of looked at me and he said, we're having a really nice meal. BGP is just, it's just like, it's going to spoil the meal. It's so complicated. He understood it to the nth degree, and he couldn't explain it certainly over a good meal. Did he know? Of course he did. But you get the idea over here, is that these protocols, if you're interested in them, oh man, just do a search on one of the search engines and you're going to find tons of information on all of these, on RIP, OSPF. And when you dig, you find more. And when you dig, you find more. And you can specialize, you can spend your life. There are probably guys, I'm sure that they are networking experts that will specialize on something like BGP. And that's all they will do. They get contracted in, set up all the BGP, and then thank you very much, off to the next project, just because that's how big a topic it is. I'm trying to cover it in a few minutes. Can I do it? No. Now, before I get onto this slide, what I want to do is the following. A while ago, Rowan and I took a trip to a nuclear bunker near London. There were 17 of them. During the Cold War, the British built 17 of these nuclear bunkers. And that was the place where if Britain was attacked with a nuclear weapon, they would, the government would be sent to these particular nuclear bunkers if they could get there in time. And from there, they would run the country, or what's left of the country, if you want to call it that. And Rowan had gone to these as kind of like he just went to visit them. And then he took a photo of something that he saw. Said, Isaac, you got to come. So we made a time to go out there, and both he and I then went there, and we did some filming within the bunker. And I've got a clip. It's about 7 minutes a clip, more or less. And what we're going to do is we're going to play this clip for you now, because it is so interesting. And I think this is a perfect place to actually fit it. When you see this clip, when you see that picture that I tell you about, that I've told you about, that when I saw it, it was like, wow. When you see that, you suddenly realize that all of this stuff, all of this routing, it's fantastic when you see it. But let me stop talking. Let me show you this clip. Enjoy it. This place is just blowing my mind. This is so amazing. We're in one of the communications rooms now. ComCen, I think, probably means Central Communications. And I want to show you something that when I saw this, it blew my mind. Take a look at this. They call this over here the chicken wire system of communication. Take a look at that, the chicken wire system of communication. Look at what they've done over here. They have all of these different sites, and look at this. They have routes between all of the different sites. Is that familiar? That's got to be familiar to you, right? We're talking about Extreme Academy. We're talking about scalable networks. And of course, the most important thing when you're talking about building seriously big networks is, of course, resiliency, building resiliency into the system. So we're better than a nuclear bunker to come and think about resiliency. Now that leads to this document. Look at this document. I'm going to read this because, it says the chicken wire system of communication. Given this nickname as it spreads throughout the country like chicken wire, connecting bunkers by many different routes, which we saw on that poster over there. Message routing, the start of routing, right, was done automatically to find the quickest route. Think about things like OSPF, open shortest path first, finding the quickest route to any particular destination. This system is now defunct, like the bunkers it connects, but it hasn't been wasted. It now forms the basis of the internet system. It now forms the basis of, this is the basis of the internet. The idea, ARPA, they needed to develop a system in case one of the major centers was taken out in the US. They had to be able to route. And here we look at, they already talking about the shortest route, finding the shortest path. This is fantastic. But come look here, come look at this. In Academy, I think it was series 1, we were talking about bits and bytes and binary, and we got to talk about packets and frames and segments and things like that. Look at this in a packet header. See this as a packet header, right? Use, routine, priority, immediate. And these were the rules. No more than 500 words. If it was immediate, well, no more than 100 words. And then it would tell us, don't use this particular box. Use NATO secret or NATO confidential in there. This particular message was sent to Ludwig van Beethoven. You can see his name over there. Brilliant, right? He couldn't hear, but he could read. So there's the message going out to him. I'm joking, but, and so this is, if you think about this, then you can understand how protocols and packets have headers with destinations and importance and these types of things. Here it is. Here it is in a written form that you can actually see this. But that's not all. Come here, Rowan. Bring that camera here. Let me show this. By the way, the teletext machine, I believe Rowan's first job was working one of these teletext machines. I know these things. Take a look at this. Pro signs used for what? For controlling traffic. For controlling traffic. Think about TCP/IP, transmission control protocol. Controlling. I mean, it tells you what do you do. Following repetition of message, the number is made in accordance with your request, and here's all the codes that you would put into there. I mean, look at this, the routes, the routes that we would that you could get these messages out. Each one of those desks is a ministry, one of the ministries of government. It's incredible that you could run a ministry, from a desk like this.
Well, Isaac, I hope everybody liked that. It's great to come to these places and just bring these things to life, show a little bit of history of the technologies. It's like what we're talking about today. It came from the past.
Yeah, it's fantastic. Thank you for inviting me. It's really when I saw that chicken wire thing, it just made it alive for me. Yeah. So yeah, brilliant.
Yeah.
I loved it.
Yeah, let's do more of this. Let's get out and about more.
Absolutely. Yeah. Absolutely. Have you got anything in Hawaii?
We could, I'm sure.
I'm
sure somebody out there has got something we could do in Hawaii.
See you in Hawaii. Cheers. Thank you. How fantastic was that video? I mean, I absolutely loved going to that place. It was just fantastic, and to see that chicken wire diagram, man, that just brought the subject alive for me. That all those years ago when they built those bunkers, they understood the possibility of something happening and the communications being interrupted. And then they designed all these different paths with different costs so that if you needed to get from point A to point B and you couldn't go direct, well, you had so many alternatives that you could take to get to that final destination. And of course, it makes so much sense. But to me, the thing was seeing it, actually touching it. It's like, this is it. This is the blueprint. If you ever get a house designed and you see those plans, it's like, this is it. From this, they built all that communication structure, and the internet, this network of networks, had its birth in something like this from DARPA in America. Wonderful. Thank you, Rowan, for inviting me to go there with you. What a wonderful event. Highly recommended. If you live in the UK, go look up these nuclear bunkers. They're absolutely fantastic places to go visit. And I know Evert Red Miles has told me that in Netherlands they have them too, and I'm sure other parts in Europe. I'll tell you what we're going to do. We're going to land it now. I'll pick up this slide next week in episode 4. So I'll pick it up from here, and we'll finish it off, and then we'll get into that stuff that I told you about when it starts to get really hairy and scary, when networking is like, whoa, and you have to almost go slide by slide to be able to really understand what this is about, and as we go deeper and deeper. So thank you again for watching, for attending, for being here. We really value your presence. Once this is finished, just like us on YouTube, whatever, on LinkedIn. Follow us on LinkedIn on our Academy Extreme Network Training account, a sub account of Extreme Networks, to hear the latest news on Academy, Welcome Series, ECS, and all our other training that we run at Extreme Networks. It's been fantastic. Thank you so much. I'll see you next week. Cheers.